We're going to look at continuity and one-sided limits, and we've talked a lot about this stuff in our last in-class lessons. So we're going to talk about continuity at a point and on an open interval. So for a function to be continuous, it has to be unbroken. This means there are no holes or jumps or gaps. A good trick is if you don't have to lift your pencil, then you know that your function is continuous. Here are some examples that are not continuous. So if I have a function that is not defined at f of c, so the actual value. So if I have something like this, and I have an x value that is c, then, and I have a graph, this, and it has a hole. This is a hole or a removable discontinuity. Okay. Next, if the limit of f of x as x approaches c does not exist, remember, what does that look like? So something like this, and then it jumps. Okay. So this is a jump or a non-removable discontinuity. Okay, and the last type is, well, here's another type, is when f of x does not, when f of c does not equal the limit of f of c. So something like this. There's a hole and then there's a jump. Okay. So this is a hole. And this is a removable as well. Okay. So what is the definition of continuity at a point? So continuity at a point. Well, there's three things that we need in order to say that we're continuous at a point. The first is that f of c is defined, or it exists. Okay. We have to say that the limit as x approaches c of f of x of the function exists. Okay. And we also have to say that the limit as x approaches c of the function is equal to f of c. So these are all the things that we're talking about. This is the actual equaling the limit value. So they have to exist, and then they have to equal each other. These are the three things, three conditions. Okay, so continuity on an open interval is a function that is continuous on an open interval a to b if it is continuous at every point. So the limit is equal to the actual on every point. Let's write that down. In the interval. The limit value equals the actual value. And then we extend that to say that this is true for all x values, or all values on the interval from a to b. So here we go. Let's look at the next one. F of x is 1 over x. So if I look at that, that's a graph. Well, where isn't this graph continuous? I know that it looks like this because it's a rational function. So I can see that what value of x is going to make us not work. So when x is equal to 0. So we can say it's continuous everywhere except x equals 0. Okay, where is this graph continuous? So how would I check this? Okay, graphically, I can go ahead and be like, okay, the top graph is a line, so we're going to start at y equals 1, and then it's that kind of slope of 1. And then the next one, x squared plus 1, is shifted up 1, and then it's just a parabola. So is this graph continuous? Yes, it's continuous everywhere. Or on the interval from negative infinity to infinity. Okay, the last one, I know from rational functions that the x minus 1 on the bottom means that x, let's just do it the same. It's continuous everywhere except x equals 1. All right? So what is a discontinuity? Is if the function is not continuous, then we say it's discontinuous. So discontinuities come in two types, removable and non-removable. Okay, so a non-removable is like a step. So something like whole and then that. So a step or a jump. Okay, and then another type is our infinite. So something like this. Okay. A removable is a whole, and it can either be defined elsewhere or not. So for the first one, it's not defined elsewhere. The second one is. Okay. These are both removable discontinuities. All right, so one of the ways that we check to see if we have a limit is by checking at the left side limit and the right side limit. So a limit can be defined for just a single point C if the left, which is the left side limit and the right side limit. So we're going to look at these separately, the left side limit and the right side limit. Okay, so the left side means that we're coming from the left, and the right side means we're coming from the right. Okay, and just because we have a right-sided limit doesn't mean that we have a left-sided limit, nor does it mean that we have an overall limit. Okay, so we denote a left-sided limit with the minus sign right here. See the minus sign? That means from the left. Okay, and the plus sign means from the right. So when it's like that little exponent, the minus and the plus from the left and from the right. Okay. So we're going to look at the graph, the limit of f of x as x approaches 3. Remember, what does that mean? That means from the left. Okay, so I'm going to go ahead, moving my cursor to x equals positive 3 from the left. I'm approaching the value of, that looks like about 1. Okay, and then the next one, b, from the right, I'm approaching the y value of 4. So in order to have a limit, remember, I have to matchy on the left and the right. So do the limit values, the one-sided limit values match? No, so this limit does not exist. Okay, lastly, what is the actual value of f of 3? That's 1. And does that match the limit value? No, so this is not continuous at x equals 3. Okay. Let's evaluate the following limits. So the limit as x approaches 2 from the left of 3x over x plus 4. And I am going to go ahead. I notice that when I plug in 2, it's not going, the graph isn't undefined. So I am only undefined at x equals negative 4. So I'm going to go ahead and just direct substitute in the 2. So 3 times 2 over 2 plus 4 gives me 6 over 6, which is 1. So the limit value is 1. The next one, if I plug in 3, I get 3 minus 3 over 3 squared, which is 9, minus 9 gives me 0 over 0. That's an issue. I know that 3 then will make me undefined, so I have to do some fancy stuff here. So let's do this. Let's factor. The limit as x approaches 3 positive of x minus 3 over x minus 3 times x plus 3. That's a difference of squares. Those factors cancel, leaving me with the limit as x goes to 3 positive of 1 over x plus 3. Now when I plug in 3, I am not undefined. So I can do 1 over 3 plus 3 gives me 1, 6. I can also check on a graph for this or a table. Okay, if I plug in 0, will I be undefined? Yes, I will get negative 1. What I get is negative 1 over 0, which is undefined. So this is not an indeterminate form. What this tells me is that I have an asymptote. So if I have 0 over 0, that's indeterminate. Something cancels. If I have 1 over 0, that's a whole nother story. So I'm going to go ahead and graph this. And I'm just going to see that the graph looks like this, something like this. So the values are going towards negative infinity. We don't say equals, actually. It doesn't equal negative infinity. We can say it goes towards negative infinity. So the limit does not exist or does not exist. These are both correct. Okay. All right. So the existence of a limit. Let f be a function and let c and L be real numbers. The limit of f of x as x approaches c is L if and only if, okay, here's the rule. The limit as x approaches c from the left of f of x has to equal the limit as x approaches c from the right of f of x. This is matchy-matchy on the left and the right. Okay, in other words, the left and the right hand limits have to equal each other. Okay. We can use this information to extend our definition of continuity on an open interval to definition of continuity on a closed interval. So brackets, from like 1 to 5. Okay. So here's what I know. If the function is continuous on the open interval a to b, so in between a to b, if this whole part is continuous, and the limit as f of x as x approaches a value from the right is equal to f of a. So that would be this. On the right, if I approach that value, then, and on the left, if I approach this y value, then I know that I'm continuous at the points. What it's basically saying is that you're continuous in the inside, the open interval, and then these two tell us about the endpoints. Okay? And that is it for today.